Hello everyone, welcome back to my channel. Or if you're new here, welcome. I thought I'd try something this year. Normally I talk about all these things in class, but I think a lot of it tends to get lost in the noise and people not paying attention when I talk, which, I don't know why, but anyway. So I thought I made a video of me going through certain issues relating to Unit 3 Area of Study 1 in preparation for the upcoming SAC. And then I'll talk a little bit about maybe some general advice in terms of what you may want to consider when you go through the SAC. So that's the agenda of this video, is just to overview the content of Unit 3 Area of Study 1. We haven't technically finished. We've done about two-thirds, but the first SAC is the only SAC for this area of study, so it's high time to sort of go through it. And I want to talk quickly about different types of questions and some common mistakes that people tend to make. And then we'll talk about the SAC structure and my advice. We'll see how we go with this. If people think this is something useful, I may try to make one every SAC, and you can watch them again at the end of the year because the content doesn't change, and a lot of the advice for SACs will probably apply to the exam as well. This is totally not a elaborate scheme to keep my channel going and for me to practice editing videos, which I think I figured out how to put music on, so we'll see if there's music playing right now. Anyhow, so Unit 3 Area of Study 1, this is a focus question. What are the options for energy production? So everything that we learn kind of goes back to this question, and there's a little bit on batteries and hydrogen gas that we're going to talk about later when we look at redox. But for the most part, if you think about it, everything that we've learned ultimately go back to this question. We're trying to answer the question of what are the options for energy production and how do we make the current process better, more environmentally friendly, more efficient, so on and so forth. So there are generally four topics under this focus question that we have covered. The first one's fuels, so dot points 1.1 to 1.12, and then we look at gases, energy, and calorimetry. So four topics, if you will. Technically, calorimetry is in Unit 4 Area of Study 2, but we always teach it here because it's a nice comparison to the original energy content experimental technique. But you will see it again at the end of the year when we look at food chemistry and energy content of food. So first topic is fuels, which are the first 12 dot points that you can find in the capacity matrix. Now make sure that you use your capacity matrix well. You can read each of these dot points properly, do a bit of self-assessment in terms of what you know and what you don't know. And I think you can also find the textbook section that is relevant to each dot point in the capacity matrix as well for the most part. But I really think you should do the self-assessment now so that at the end of the year, when you come to revise for the exam, at least you can quickly identify which area you need to start first based on your initial assessment. So the first three set of dot points look at just basic definitions, essentially. So definition of fuel, renewability, sustainability, and then the definitions of some of the key physical properties that we tend to look at for this topic. So cloud point, flash point, viscosity, hygroscopic properties. And you need to understand the basics of how do you describe and compare the differences in these physical properties, which basically comes down to intermolecular forces. And then you need to be able to describe the formation, sourcing, usage, and impacts of fossil fuels. Generally speaking, three types of fossil fuels. You have the solid version, which is coal, which we seldom talk about to be honest, but it's there, it can come up. Crude oil is the liquid version, and then you have a range of fuels that you can get from the fractional distillation of crude oil, and gas. Now it's methane, but it could be natural gas, shale gas, coal seam gas, and of course you have your LPG, which also comes from like the gas component of crude oil. So you need to be able to describe how do you get each of these fuels, what do you use them for, and what are their specific impacts, because they don't have the exact same impacts, some of them. So you really want to see whether you can distinguish between the different fossil fuels. You have to be able to do the same for the biofuels. So we're talking about formation. In this case, really the synthesis, because biofuels are made ourselves, so we don't just extract them like fossil fuels. And then the sourcing, the usage, and also the impacts as well, good and bad, because renewable is not automatically better. There's a lot of nuances in this topic that I think the hope is that you can get, so you know a little bit better about the whole fuels idea compared to the layperson. And then I think the crux of this topic is really the comparison between fossil fuels and biofuels. And I'm sure you've seen the majority of questions going in this direction. I mean, I seldom ask you to define what a biodiesel is, but it's always a comparison. So you need to be able to evaluate the suitability of using these fuels in different scenarios. Okay, so that's the last three dot points. I think the majority of assessment questions fall into these three dot points, but you kind of need to understand all the other dot points in order to do the last three. All right, so just a quick reminder. I think I just mentioned a lot of these already, but for every fuel, you need to be able to tell me the chemical structure. This is chemistry after all. So if I ask you what is biodiesel, you need to be able to tell me that it is fatty acid metal ester. I think if I give you a bunch of formulas, I do expect you to be able to recognize which one is biodiesel, but I don't expect you to be able to write the formula yourself from the starting materials just yet, simply because you probably need to revise esters and esterification. But by the end of the year, you're going to be able to do that, and you're going to be able to write an equation for trans esterification yourself. Physical and chemical properties. So the physical properties, as mentioned earlier, are just the hygroscopic properties, flash point, cloud point. Chemical property is really just combustion. So the only thing you need to think about in terms of chemical reaction in this case is complete versus incomplete combustion. So make sure you can write the equation for the complete and incomplete combustion of each fuel. Obviously, incomplete combustion, I need to tell you whether it produces carbon monoxide or carbon or a combination of both. But the key thing is just to be able to balance the equation properly. The production, so this includes both extraction and synthesis and usage. Generally, two main usage for fuels: electricity and transportation. You need to know what fuel is used in what scenario, and maybe think about why that fuel is generally used in that context. So methane is used a lot in heating and cooking, but you don't really see it as an fuel for transportation because it's a gas in the majority of cases, and it's quite difficult to have a gas as your fuel for a car because you need a large volume for the tank in order to have like a decent amount of fuel in there. So if you want to use a gas as fuel for transportation, you really need to either put a lot of pressure so you can compress a lot of gas into the tank, or you have to have some other form of storage. And this is actually something we're going to talk about later when we look at hydrogen cars, which is the next big topic for redox. If you want to use a fuel for electricity, you really need it to be very energy dense as possible, which is generally why coal is the number one fuel for electricity, at least in Australia. Methane, you could use it, but you probably won't get as much energy out of it, so you need a lot of methane. So it's a good supplement, but it's probably going to be impossible for methane to completely replace coal as the fuel for electricity. So really think about all the nuances as I this is the second time I've said that word. But relating to why certain fuel is used for certain purposes. Pros and cons, obviously, relating to production and usage. Try to branch out and maybe not talk more than just environmental impacts. So there are other things like ethical issues that you can talk about. Mentioned a little bit on the usage already, why something is used for this and not that. So, there's a lot to talk about. And I think if you dig deep, there are many, many interesting ideas that can come out of a lot of this. One way to quickly revise for each fuel is to draw a system map that we showed you when we first introduced you to this topic. So the whole idea of the system map is just so that you can quickly summarize and revise each fuel without having to rewrite every single point out. You can make the map by yourself or with other people, and you can make a quick comparison that way. Okay, so that's the fuels. In terms of the main types of questions that may be asked, I would say the describe and explain is probably the number one. So describe and explain the difference in insert any physical property between one fuel and another fuel. Very simple 3 mark question. I think this should be your bread and butter. You should all aim to get full marks for these questions. I think they're pretty simple as long as you know what the fuels are and what the physical property is. So if you don't know what hygroscopic property is, it's kind of very hard to recover from that. If you don't know what biodiesel is, also very hard to recover from that. But other than that, it's very easy to get the marks, I think. But you really want to aim to get full marks, especially if you know what you're talking about. So a couple of things to keep in mind. This is not going to be the only time I say this, but you want to be as specific as possible when you write your answers. What do I mean by that? And this happens every year, no matter how many times I tell people. You want to tell me the name of any intermolecular forces involved. So when you do an explanation of, let's say, why a fuel has higher boiling temperature than another fuel, you are going to make a comparison of intermolecular forces, but you have to tell me what is the intermolecular force in question. Is it dispersion force, dipole-dipole, or hydrogen bonds? If you just write intermolecular force, there's a high chance that you will not get full marks. Sometimes people just write bonds, like the bonds are stronger, like which bonds? Covalent bond, metallic bond, ionic bond? I don't know. You have to tell me what it is, okay? State the name very, very clearly. Also say it correctly, because if you say it wrong, you also lose mark. Which is my second point. Think very carefully in terms of what intermolecular forces should be present depending on the situation. Sometimes you students write like this beautiful answer, everything's perfect, but then they make one incorrect claim, like something is non-polar, and they say, oh, it can form dipole-dipole interactions. I cannot give you full marks if you make an obvious mistake like that. So you have to be specific, but you really want to take the time and think about what kind of bonds can be formed in which situation. When does something have hydrogen bonds? When does something have dipole-dipole interactions? If it is non-polar, it can only form dispersion forces, so don't even bother writing any other name other than that. You should know if something is non-polar or not. Okay, the second thing, or third thing, if you will, when we talk about being specific is if you have time, it's a good habit to try to incorporate the definition of the property being discussed in your answer. And I've noticed this done a lot, very well in a lot of answers I've read. So well done, and keep that up. What I mean by that is you kind of want to you want to have a difference between your answer for flashpoint and your answer for cloud point, because at the end of the day, your answers will sound very similar for the most part, because you just say, oh, something is longer, so has stronger dispersion forces, yada yada. But the actual describing of the difference, you can try to incorporate the definition of it in. It just sounds a little bit better. It sounds that it shows that you know what it is that you're talking about, and this is not just a generic answer that you memorize and use in every situation. So, for example, if I say that biodiesel has a higher flash point than petrol diesel, I could include the definition of flash point at the end, which so it means that more energy is required to turn it into gas. So I've shown that I know what flash point is. If the question is asking for cloud point, you can also tag in like a little bit of a definition of what cloud point is, which means that it solidifies at a higher temperature. Sometimes this is useful, sometimes you don't necessarily need it, but I think it's a good habit just so that you show a little bit more understanding of what is being asked, and it gives you a complete answer. If you run out of time, just skip it, that's fine. Remember that I think more important for the exam, you are assessed on what you show on the page. So if you can show just a little bit more understanding, it's generally better. You never know what marking scheme they will come up with depending on the year. So that's what I mean by be specific, okay? Second type of question, which is probably like a advanced version of the first type. You're still making a comparison, but you have to be a little bit more meta, if you will. Maybe not that. That's not the right word, maybe. But you need to compare the usage of fuels in a specific context. So the first part is the comparison. Sometimes they're not very specific in terms of what comparison they want you to make, but you need to be aware of what comparison is actually suitable. So if I talk about biodiesel, like the usage of biodiesel in a context, I am technically comparing it to petrodiesel because you are using biodiesel as a replacement for petrodiesel. If you were talking about biogas, it is generally to replace natural gas or shale gas or coal seam, so the non-renewable version of methane. If you're talking about bioethanol, most of the time it's going to be in a blended form like E10 or something like that, and you're comparing it against regular pure petroleum that is being used. So the comparison has to make sense, okay? Don't compare a fuel with something else that you never going to replace it with. So that's really important. You have to compare the fuel with the immediate alternative. So for example, if I say something like one disadvantage of LPG is that it has less energy than petroleum, you probably won't get the math for this. It's not wrong, but it's just not really, it's like a feature of LPG, but I wouldn't go so far as to say that it is a disadvantage of LPG because we're never going to replace petroleum with LPG anyway. So a few LPG has less carbon, it has a lower energy content. That's a feature, it's not a disadvantage. Mainly because LPG and petroleum shouldn't be compared with each other. They generally have different purposes. You wouldn't use LPG in a car, well, most of the time, you use it for like camping and stuff. So you can compare LPG to, say, biogas or natural gas. At least they both gases, but I wouldn't actually make this comparison. And I've noticed it in some of the answers I've read. So you can't really claim that something is an advantage or disadvantage unless you compare it with the immediate alternative that you're supposed to replace it with. Okay. Another example that I think it's also not really good is to say one disadvantage of biodiesel is that it releases CO2 from combustion. Again, it's a feature. Is it a disadvantage? It's not really, unless something else can supply energy without releasing CO2 from combustion. So if you have two fuels, they both release CO2 from combustion. It's just not the best answer. I wouldn't pay it either because it's like stating the obvious. This is only a disadvantage if you are comparing it against a fuel that does not release carbon dioxide from combustion or does not release carbon dioxide during its usage, which, fun fact, we actually will talk about that later, but until then, don't just bring this up, okay? So think about the alternatives. If something is an advantage, it must be because the alternative cannot do it. If something is a disadvantage, it's because the alternative has something better. So don't compare apples to oranges. Make sure you know what is comparable to what. The other thing, oh, actually, I have some more things to say about comparison. This video is going to be long, folks. When making a comparison, show both sides that you are comparing. I've seen some really good answers that have done this, so very good. I think much better than what I normally see at this time of the year. So if you say biodiesel is good, you also want to tell me that petrol diesel is bad in your answer. So it shouldn't, try not to imply things like this is not English. So I kind of need to see everything, especially in the exam. They don't know you, so you have to show all that you know. The other thing that I want you to be very careful of, and I've noticed a little bit of this, especially reading students' responses, is sometimes people repeat themselves twice. And this is because a lot of time people try to go with the one idea per mark, so they try to write two things. But sometimes you kind of repeat yourself twice. An example of this is when the first line you say A is less than B, and the second line you say B is greater than A. That's only one idea that you've shown me. So try to not repeat yourself. I give you an example of what it looks like. So let's say you have the question of explaining why biodiesel is more environmentally friendly than petrol diesel. So this is a first mark. Biodiesel is more environmentally friendly because it's more carbon neutral, and then you go on and explain what carbon neutrality is. So that's good. You will get 1 mark for the first sentence and the second sentence. And then the last sentence, sort of to talk about the other side of the argument, the student says, by contrast, petrol diesel is less environmentally friendly because it is not carbon neutral. You really want to try to avoid doing this because you kind of just restate the first sentence but flip it. So you haven't really given me any new idea. I can say this even if I don't know what carbon neutral is. I mean, I can assume that if something you're trying to say that biodiesel is more environmentally friendly, so I could just logically reason my myself into the second sentence and say, oh, well, if something is less environmentally friendly, it may be because it's not carbon neutral. Instead of saying this, instead of saying, oh, A is good because it has it, B is bad because it doesn't, tell me what B has instead. So this is also going back to the point of being specific here. So instead of saying because it is not carbon neutral, maybe you can tell me because it comes from fossil fuel, and then so whenever you burn it, you just release CO2 into the atmosphere. So you're basically explaining what being not being carbon neutral means, but without actually saying that, because I want to see more information that is given for the last mark. That is not just a simple rewriting of the first sentence, okay? So try to avoid saying yada yada is, you know, good because therefore the other, which is the has the opposite property, is bad, if possible. Oh, this is probably not the end. You want to continue, but you kind of want to tell me what not being carbon neutral is. Don't just assume that I can just flip the first bit that you say. Anyway, that's what I mean by not repeating yourself twice. It's not the most like serious of issues compared to not being specific or not saying or saying intermolecular forces and not telling me what the bond is. So in some cases you can get the mark for it, but I again would advise against doing it, and hopefully you can be a bit more specific in your answer. All right, the second thing to sort of talk about is the specific context part of the question. You've seen two of these, I think, at least in your homework booklet. So the first one is the marine diesel question, and the second one's the mass question. So as the name suggests, if a context is given in the question, the the hope here is that you can include the context in your answer. It's very hard to train for this because we don't know what the context will be given, and some people just naturally better at some context than some other context. I think one year there was a question on redox, and the context was portable devices, and you had to identify that lithium is used because it's light, and you have a portable devices, you want your battery to be very light. So you have to really think about the context, and people tend not to do that very well. Just keep that at the back of your head. Try not to stress out too much. Even if you can't think of anything, just talk about generic stuff, so at least you can get some marks for the question. But in general, especially with the context type questions, tend to have like a four marker when it's slightly open-ended and you have to talk about different things. The rule of thumb is still 1 mark per idea or comparison, depending on what you have asked to do. So if it's a 4 mark question, try to give me 4 points. It could be like 4 small paragraphs, but you want 4 points, okay? If you can't, as I mentioned earlier, if you can't link every single point back to the context, aim to link at least a couple. And sometimes it is quite difficult to link every single point in your answer, especially if you have like a 4 mark answer. Like last year, the last question was 8 marks. It's very difficult to link every single point back to the context, but aim to link at least a few. So we go back to the marine diesel question. Well, if you use a fuel under the sea, is quite cold and there's a lot of water, so you straight away should talk about flash point or cloud point and hygroscopic property, and then that's a nice one for you to link back to the context. The Mars question has heaps of things because there's a lot of information on Mars that was given in that question. I think the Mars question you definitely can link every single point back to the context. If you haven't already, you may want to try to redo that question and try that. The other thing is you want to aim for a breadth of ideas. So instead of just have every single point on physical properties, you kind of want to do a little bit of everything. Again, remember, especially for the exam, you want to show what you know. So you want to show that you know not just about the differences in physical properties of the fuels or the environmental impacts of fuels, but you know all of it. So let's say if the question's worth 4 marks, like the mass question, I would plan 1 mark for physical property. So I don't know, I can say, oh, Mars is really cold. So if you use biodiesel, it's probably not going to flow very well. It's going to be very hard to burn. So it may not be that feasible. 1 mark on usage, you can pick another fuel because you can, and you say, oh, Mars doesn't have a lot of oxygen. So it's going to be very difficult to combust these fuels, like any of them really. One mark on production. So you can pick something else now. You say, well, if you want to make biogas, you need to generate a large amount of organic waste, which is probably going to be difficult in 6 months, especially if you want to make enough biogas for use, because you would need a fair amount of waste. So that's a points against it. And you can say, oh well, if you want to make biogas, is anaerobic decomposition. So the condition on Mars is actually quite good, because it had very high amount of carbon dioxide, very low amount of oxygen, so you definitely could use it for that. And then one mark on environmental impact. I don't know. I think the Mars one's probably a bit hard to do with the environmental impact. You could sort of talk a little bit on carbon neutrality here. The fact that if there's a lot of CO2, let's talk bioethanol, because we haven't mentioned bioethanol. So when you grow sugarcane or whatnot, photosynthesis is going to absorb carbon dioxide, release oxygen, and then later on when you burn it, the opposite happens. So you don't contribute any extra carbon dioxide into the atmosphere, which is probably a good idea since you don't have a lot of oxygen in the first place on Mars. So for Max, try to give me a little bit of everything. Give me a little bit of this of fuel, a little bit of that fuel. So it shows that you know more than just this one fuel or this one issue. Okay. If you have time, do more than four. Do six in the sack, and I think a little bit of the exam as well. We go with like the best answer, get the full marks. So go with more if you have time. If you don't have time, that's fine. Do the rest of the questions and then come back. But if there's 4 marks, aim to go like six if you can. Very important, just like any good essay, you want to plan your answer before you write. So have a quick, it doesn't have to be like an elaborate, like actual essay plan, but like have a quick thing. All right, I'm going to talk basically what I just said, physical property. All right, we have flashpoint, cold temperature, biodiesel, usage. All right, biogas, I don't know. So have a bit of a plan. So sometimes people just do like one, two, three, four, and then you can just quickly write like two or three keywords, and that allows you to remember what you're supposed to say, and allows your whole answer to be more coherent to read. And I've read some really enjoyable pieces of writing from this. So if you claim that you're good at English, and not targeting anyone in particular, I'm prepared to be impressed. Okay. Oh yes, this is just only the second time that I tell you to be specific, especially for the math question, which I've read a couple of answers. Don't just say the fuels or the biofuels. You've learned like at least 8 or 9 different types of fuels. Tell me which fuel you're talking about. They're all slightly different, and you actually show a better understanding if you can distinguish between the different fuels. So please don't just say the fuels, the fossil fuels, or the biofuels. That just makes me sad. Anyway, that's the first part on fuels. This video is going to be long. I'll do chapters or timestamp or whatever. Here's some music, which I need to find. Anyway, so the second topic is on gas. There's only 3 dot points. It's really 1 dot point. It's just stoichiometry using universal gas equation. Generally speaking, gas is really easy. You can use the universal gas equation, you'll be fine. Where's the universal gas equation? It's in your data book. Although you can use SLC condition molar volume as well if you want. So general form of question is just find number of mole, mass, volume, pressure, temperature using universal gas law. Can't really tell you what they can ask. There's some really interesting stoichiometry once in a while, but it's generally pretty simple. Thing is just to be careful with units. So you need to be aware of what units you need to use for each of these. So pressures in kPa, volume is in liter, and I think the main one that people sometimes forget is the temperature has to be in Kelvin and not Celsius degree. But if you do that, you're generally going to be okay. Transpose properly and all that. The other thing that sometimes people make a mistake, generally not now, that generally happens like at the end of the year when you revise for the exam, you've forgotten everything, and you have so much more content on top of this. It's you can only use universal gas law for gases. Out of desperation, I've seen it used for like an aqueous solution, which is quite sad. Don't do it. All right, just look at the stats. If it's a aqueous, don't use the universal gas law. Just saying. Um, just sort of another thing I want to talk about, because gases in itself is a pretty easy topic, but remember that everything has to fit back to the context, which is what are the options for energy production? That is the question of this area of study. So you really want to think about how does gas connect to other things that you've learned, like fuels, energy, calorimetry. So some gases are fuels, so you can use universal gas law to talk about the amount of, say, methane gas that I need for this in volume, or the amount of LPG that I need for this in volume. So there are ways to connect energy and gas quite easily. But the main one that I want to talk about here, which to be fair doesn't happen very often, but when it does, people tend to struggle because it doesn't happen very often, is when you have to link gases and then use it to discuss the amount of greenhouse gases produced from the combustion of fuel. And there's a lot of things that can be asked here. Well, not a lot, but there are a few things that I can ask. I mean, I could ask you for the volume of greenhouse gases that comes out of a complete combustion of any fuel under SLC, or any fuel, and then I tell you temperature, pressure. First thing I want to remind people is that if H2O is written in gas form, so if we're talking steam, it is a greenhouse gas, which seems like an obvious thing to say, but I think a couple of years ago, some people kind of forgot this, so here's a reminder. And the second thing that I think is very useful to remember is that the amount of carbon dioxide produced from combustion can be found using the fuel's formula. So you don't have to write and balance your combustion equation to work out how many mole of CO2 should come out of combustion of 1 mole of fuel. So for example, if I have octane, which is petroleum, so if I burn 1 mole of octane, which is C8H18, because there are 8 carbon in the formula of the fuel, it means that it's going to release 8 mole of CO2 from its complete combustion. With incomplete combustion, you would need to write an equation because I don't know. It really depends on how much oxygen is available, but they tend to just ask for complete combustion. So if the combustion is complete, you just need to look at this. If I have, I don't know, C13H28, whatever that is, some form of kerosene, I think. If I have 1 mole of that, that's going to give you 13 mole of CO2. Simple as that. So you don't have to necessarily write the equation of combustion to work out how many mole of carbon dioxide should come out from the combustion of 1 mole of a fuel. Okay. Um, the other thing I want to talk about is you have to be very careful when making claims on the amount of CO2 produced during combustion of a fuel. Do I have an example? Okay, so let's think about this statement that some students, for example, make a claim. So maybe someone say bioethanol is more environmentally friendly than petrol. So sometimes people take this angle when talking about environmental impacts, because this is a good way to actually discuss carbon dioxide emissions. So you can actually provide evidence of something has more carbon dioxide released from its combustion than something else. Let's say, so the statement is bioethanol is more environmentally friendly than petrol since combustion of 1 mole bioethanol. Now, bioethanol is C2H5OH, produces 2 mole of CO2, so that's correct. So that's 2 carbon here, compared to 8 mole for petrol. Now, I just mentioned earlier, petroleum is octane, so the ratio is correct. So the claim made here is that if you burn 1 mole of ethanol, it only produces 2 mole of CO2, whereas if you burn 1 mole of petrol, it produces 8 mole of CO2. Hence, ethanol contributes less CO2 to the greenhouse effect. That is actually not a very good claim to make. I would advise against doing this. And the reason for that is because when you compare the amount of carbon dioxide released, instead of comparing the amount of CO2 released per mole of the fuel, you need to think about the amount of energy released, the amount of CO2 released per kilojoules of energy that's formed. Because yes, you produce more CO2 when you burn petroleum, but it's about how many mole of it do you need to burn to get the same amount of energy. So if you think about ethanol, so 1 mole of ethanol, okay, I'm just going to use a formula, produces 2 mole of CO2, and it's going to produce, okay, let's just write it, 2 mole of CO2. And if you look at the heat of combustion, this video is going to be 100 years long at this rate. It's 1,360 kilojoules. So the molar heat of combustion is 1,360 kilojoules. And then you look at 1 mole of octane. Do we even have octane in here? Yes. you have 8 mole of CO2 and 5,460 kilojoules of energy. And then you can work out the amount of no, we'll see what happens. So 0.00147 mole of CO2 is released per kilojoules of energy that you get from ethanol. And then in the case of octane is 0.0014. I mean, I'm nitpicking here, but it is slightly less. So you actually release slightly less CO2 for every kilojoules of energy that you get from octane when compared to ethanol. So you can't really say that ethanol is more environmentally friendly than octane if you're taking this angle. Like you can say it's more environmentally friendly because you absorb some CO2 when you make bioethanol, but if you just think about the fuel, it's actually not very good. Like it gets the same amount of CO2 per kilojoules. So be very careful. Be very careful when you're making claim relating to amount of CO2. You can do it. Actually, when done well, it's a pretty you know interesting and novice way to discuss things. And when we have to read the same things multiple times, it's quite nice to read something different. Just do it well, okay? Otherwise, I can really tell that it's incorrect. All right. That's all I have for gases. The third topic is energy. Here, all the dot points. So, a lot of calculations, really. This is one of the more calculation heavy topic in this year's content. So you can read this yourself, but we'll go everything. I don't even split it that much. It's all energy stoichiometry. So we look at energy profile diagram, which we look at in more details in the next topic. Not in more details. We look at it again in the next topic, and then we look at endothermic, exothermic reactions, thermochemical equations, and then there's a lot of calculations. And that's a little bit on experimental design. So it's really not the first setup, but it's the first main setup that you need to know, which is the setup for measuring energy content. We have done a setup on gas, which I don't think will come up. So this is the first main one. All right, general types of question. Write combustion equations. Please make sure it's balanced. Don't break my heart and my not balanced an equation. It's a year 12 chemistry student. Easy way, balance carbon first, and then balance hydrogen, and then balance oxygen. You can use fractions if you want, but please check that it's balanced. Students tend to forget occasionally when there's oxygen in the fuel, they forget to subtract that from the overall. So just do some practice, get faster at it, okay? Second type of question is to write thermochemical equations of combustion reactions. So you need the delta H, needs to be negative if it's combustion. Common mistake generally only happens at the end of the year is people forget to write the delta H because they forget what a thermochemical equation is by that point. This one doesn't happen very often. You may be asked like add subtract. Generally, take multiples of thermochemical equation. So if I reverse the equation, delta H becomes from positive to negative and vice versa. If I double the coefficient, you double delta H, things like that. Normally it comes in like a question with the equilibrium constant that you will see later. So yes, as I mentioned earlier, please balance your equation. It's embarrassing. It's an embarrassing math to lose. So spend some time to do it well. Just do it perfectly. Like just do not write an equation that is not balanced. Okay? Like just don't. State is the other one. Please be careful. It's like a 3-mark question. For like an equation, you get state, you get the correct reactants and products, and it's balanced. Like it's the easiest 3 marks ever, and yet so many people lose it. So regular combustion normally is H2O gas. If you are writing a thermochemical equation under SLC, then H2O is liquid, especially if you use delta H value from the data book. So that's the main difference. Please don't go and do something weird like methane liquid. I think a lot of the fuels, the states, you can find on page 10 of the data book. Otherwise, just use common sense. Like, I don't know, diesel is liquid. Common sense. You should know this, as they say, or as I say. Don't forget to include the psi for delta H. A couple of times I've seen people forgetting negative when delta H is asked. It's not always negative. There are endothermic reactions, but if it's combustion, then it is negative. The unit is going to be kilojoules per mole for delta H, okay, always, regardless of what happens. And obviously, last but not least, is to be aware of the coefficient of the fuel in the thermochemical equation. If it's a 2 or 3 or whatnot, then you have to update your delta H because it's not per mole anymore. All right, second type, well, not second, like the other types of questions all have to do with this setup or variation of this setup. You can put a food here, obviously. So determine energy content of fuels. I mean, you think about it, there's only so many things I can ask. So you have E equals mc delta T from the water, and then this one's probably a version of energy times delta H or something like that. So you can ask for energy content of the fuel, which is the classic. I think that's the experiment that we did. But I can also give you a fuel, like a known fuel, and then I ask, oh, okay, so what would be the theoretical change in temperature if all of this fuel is burned and this is the amount of water that's there? Percentage efficiency and energy loss is another one that can come up. We've done a few questions on this. Main thing is sometimes people forget that it is percentage loss and that's the amount that's gone. So you just have to read the question. Rule number one, read the question. And then you can have questions relating to the design of the experiment. We're talking errors, accuracy, precision, things like that. There's like a whole dot point PowerPoint on it, so read that. But I think if you do the report write-up, that's probably going to help sort of have a good understanding of the common issues with this technique, which there are not that many, but there's some really key ones, like heat losses routing has to be discussed for the most part. So in general, with these kind of questions, you have to be aware of units and also the conversion of units. And I think this obviously go, kilojoule and joules, probably the main one that you have to do, but also conversion between different energy units. So we're talking, let's say, between kilojoules per mole and kilojoules per gram and kilojoules per mil. There's actually some terminologies for this. So this one's called energy content. I actually can't remember what the other one is called. I think it's energy density or something. They always come up with density when it's like per milliliter, but you can call all of them energy content. It's fine. So you have to be able to go from one unit to another, like, or at least be aware of what other piece of information you need in order to convert from kilojoules per mole to kilojoules per gram, from kilojoules per gram to kilojoules per mil. I think the conversions between energy units tends to be an issue with a lot of students. The joules one's important because mc delta T will give you energy in joules, and a lot of time you need to find the energy content in kilojoules, so you need to make sure to do a proper conversion somewhere in the question. Okay, goes to my second point. You need to know how to use density, which is just a ratio between mass and volume of a substance. um, Please don't assume that everything has a density of 1. So I think I was marking one of the homework booklet questions. Just because something is 80 liter doesn't mean it's 80 kilograms. The density will be given in the question. If you have to make that conversion, you just need to look for it, okay? Think about when to use kilojoules per mole. I have seen a couple of cases where people just write kilojoules per mole as the unit anyway, but it's not always kilojoules per mole. I think generally speaking, you only use it for delta H or if something is actually a molar heat of combustion. So don't just go and use kilojoules per mole if they ask for the energy content of like 5.7 grams or something, because that's not per 1 mole. Unless the molar mass is 5.7, but I can't think of any fuel with that molar mass at this point. So don't just use it without thinking about why. A molar heat of combustion. Do I have anything else? I think I might have something underneath. I can't remember. Oh, yes, of course. Oh, yes. When discussing errors, try to be as specific as possible. Hold on. Combustion. What do I mean by that? So, heat is losses routing is not bad. It's really not bad. But if you remember, if you have time, elaborate further. So, heat is losses routing. So, delta T is underestimated. Something like that. So you kind of want to link it back, like if you can, link it back to the actual quantity that is being affected. So when you do the calculation, it's mc delta T. That's the calculation that you use. So the reason why heat is a lossless routing is a systematic error is because it undervalues or underestimate your delta T, which in turn underestimate the energy absorbed by the water. So you could extend that line, which is nicer. I mean, 1 year, I think they actually wanted you to say that. Like, if you just wrote heat is lossless routing, you didn't get any mark. So they have been strict before. The second one that also have been penalized in the past is just say conditions are not SLC. I will not accept this. I'm saying this right now. This is way too vague because SLC have a few conditions. So 1 mole per liter is SLC, 25 degrees Celsius, SLC, 100 kPa is SLC. You want to give me at least one example of which conditions is not SLC. So, for example, you can say conditions are not SLC since temperature, the temperature is, I don't know, 20 degrees instead of 25, or the temperature is not regulated or capped at 25. So you have to give me a specific example of at least one specific condition that is not under SLC. Don't just say conditions are not SLC and leave it at that. I may not give you the mark. Probably will not give you the mark. Later on, when we talk about redox, there's some other non-SLC conditions that I should say SLC conditions. Some of the non-SLCs that you need to be aware of. So you need to know the specific ones that are not under SLC, okay? All right, last but not least. Oh my god, it's the end of this video. How long is this? Like 1 hour. Calorimetry. So we have 6 dot points only. Then the main issue is calorimetry is people forget it exists. But you need to be able to sort of do some, like, recognize the key features of a bomb calorimeter and, you know, calibration factor and all that. It's a little bit on experimental design as well. However, we don't actually do an experiment with a bomb calorimeter, so I wouldn't stress too much, but it can come up. All right, main type of question. Find calibration factor is the first one, and then use that calibration factor to determine energy content using a bomb calorimeter is probably the most typical type of question. You might be given a temperature time graph, especially in the calibration technique. You know, I have to take that back. When I said that we don't really do an experiment with bomb calorimeter, it has come up like as the experimental design question in an exam 1 year. You just need to adapt to situations, as we say. Compare calorimetry with the other energy setup, which is the one with the the water can. So you need to know why calorimetry is better. We've talked about this in terms of the limitations of the original setup that this fixed, so you need to be able to make an argument for calorimetry. Again, be aware of units. I think the common mistake is to not include units. Actually, that's just bad habit in general. Always include units. But people tend to not remember the unit for calibration factor. So it's either joules per degree Celsius or kilojoules per degree Celsius, depending on the amount of energy that's given. And unless the question specify a unit, you can use either of these. So if something is in joules, you don't have to convert it to kilojoules. If something is in kilojoules, you don't have to convert it in joules. It just has to be correct. Okay. Very common question in an exam is they would say find the calibration factor, but they don't specify what unit is required. That means that if you don't have a unit in your answer, you will lose at least a mark. The other thing when we talk about beware with units, I really only have one point here because I think I've covered most of it before, is if you want to find energy in terms of voltage, current, and time, which I think the physics people probably have a little bit of an advantage here because they've seen this energy is going to come out in joules, okay? You have to remember that. You cannot work it out anyway. The data book doesn't tell you that it's in joules, so you have to keep that in mind. Speaking of the data book, the other thing, the last thing, almost there, almost at the end. I still have some other more yapping to do with the SAC, but few pages, just make sure you know what is in it. So page 5 is great. Has a lot of good stuff. I've mentioned this earlier, but I'm not a huge fan of this calibration. Like, it's a good formula, but it only covers electrical calibration. So you still need to be able to find a calibration factor from the chemical calibration version as well. You know, you even have percentage yield. Don't worry about atom economy. We'll come back later, like term 2. Page 6, also quite good. This one is not useful, like the matrix prefixes. So, you know, megajoules is sometimes, I think there's a question with megajoules in one of the worksheets, so you need to know how to convert from mega to kilo. Trigger just to look at like the gap between any of the prefixes. So this is just 10 to the 3 if you want to go from kilo to mega. Obviously, conversion for gases are very useful here. And obviously, page 10 is the last one that you need with all the lovely stats for all your fuels and then some other fuels. Heat of combustion in kilojoules per gram and kilojoules per mole. Like, what more can you ask for? Also, read the bit at the start. I think I read this in class, but you want to make sure it even tells you it's SLC. Obviously, H2O is liquid. Okay, so that's the general overview of area of study one, or the part that we've learned anyway. Or the redox video is going to be so long if I get to make one. So let's just quickly discuss the SAC a little bit. In terms of structure, this is in the SAC notification, so you can read it then. So this SAC is basically Unit 3 Outcome 1. So it's 50% of Unit 3's max, or 8% of the study is called unmoderated, of course. Generally gets scaled up a little bit when after the exam. So the format is analysis and evaluation of stimulus materials, which is the vaguest of vague that I can ever tell you. But there will be no multiple choice questions. I know in year 11 a lot of assessment had multiple choice questions. We will not have any. You will be presented with unfamiliar stimulus materials relating to energy source, one or many. And you may be required to use the material to do these. So analyze chemical reaction, energy transformation, perform calculations, evaluate energy sources. So there will be some evaluation. Make predictions about scenarios, and I've added a little bit on experiment relating to the energy sources as well. So the whole SAC is going to be on a scenario, okay? Which means that every question is useful and the questions may be related to each other in some ways. I give you an example of last year's SAC, which you really should do at some point. The very last question, in order to get full marks, you need to actually pull from your answers from previous questions. So the whole SAC is related. It's not, okay, question one doesn't have anything to do with question three, doesn't have anything to do with question two. So you really want, especially when you talk about the big evaluation of the suitability of using this fuel in this context, you really want to think about every single question that came before. So don't just say things off the top of your head. Think about, why did I give you this particular question as question one? Why did I ask you to do this as question two? How would you be able to use it for question three? Wasn't an issue wasn't an issue, but only the top students really were able to do that last year. So you really want to think about that, okay? Now, the SACs out of 33 marks, I think that will stay. You get 5 minutes of reading and 43 minutes of writing. So, my general advice, my first advice, is you want to use your reading time very wisely. You're going to be given reading time for every SAC this year, and this is just so that you get into the habit of using it, because you get 15 minutes in the exam, and you want to really think about, like, can I use it properly? I generally advise that in the 5 minutes, that you can come up with a plan in terms of which questions you're going to tackle first and which you're going to leave until the very end. At what point do you need to finish this question? So if you have 33 marks, then after half an hour, you need to do at least 20, if not more. So you want to think about time. You think about, have a plan of, okay, question one is 10 marks, so I can spend 15 minutes on it, and after 15 minutes is up, I'm still on question one, I really need to make a move. A very common issue with year 12 SACs in general is that people ran out of time. So I think people can do really well if I just give them 2 periods instead of one, but alas, that's not what you're going to get. So you really need to think about what to attempt first, when to skip what, and be very, very mindful of time, okay? Um, okay, let's continue talking about time. It's okay if you can't answer the whole SAC. The SAC is quite long, I think. So it may be that you cannot attempt every question, but your goal should be able to attempt all the questions that you can attempt. So you don't run out of time on something that you haven't even read, and haven't deliberately skipped. Or try to keep that to a minimum, okay? The first SAC is going to be a bit shocking. I think you'll get the hang of it eventually. Check that all final answers have units. Another very heartbreaking thing is to lose random marks because you forget units here and there, you forgot to convert, you transfer the wrong number, which has happened. So, I mean, you will be calm if you're prepared. That's generally how people stay calm under pressure. So if you're not prepared, this SAC's going to whip you in the face. Let me just tell you that. 1 mark per idea. You do not have time to sort of ramble, so you want to be succinct as much as possible, okay? Be specific, but be succinct. How do you get both? No, that's your plan to find out. Well, that's for you to find out. Make a plan for long context-based questions. I've talked about this before. It generally sort of minimize students rambling and then repeating themselves. You do not have time to repeat yourself, and you do not get the math twice. So definitely do the practice set. You get one practice set, which is good under SAT conditions. So I would say do all the practice questions and make sure you at the point when you think I am ready, like I can do the SAT now, and then do the practice SAT under that condition. Give yourself 5 minutes reading time and then writing time and see how you go. Okay. Happy to read some of the answers, especially with the last question. But yeah, I think you'll be fine. You just need to do all the things by next Thursday, and then you'll be good. All right, email me if you have questions. Do not comment under the video. I will not read it. So if you have actual questions, email me. And if you make it this far, well done, claps, and see ya.